Hello and welcome. Enrichment, the area of the triangle. Yes, you heard well. The area of the triangle is the topic of the conversation today, but with a twist, not something that you would expect. Of course, I'm not going to teach you or prove to you that the area of the triangle is a half base times height, and neither will I be doing the trigonometric area of the triangle. But this is a kind of problem that appears a lot in coordinate geometry with lines and this kind of stuff, conic sections even in later on further maths, and many other problems. And a lot of people do not know how to handle it. So let's look at the problem. I'm going to put some random coordinates up there. Let's say point A, let's say 2, 2, point B, 5, 10, and point C, let's say 11, 6. I should really have put some negative coordinates, but we don't lose generality, although there is a little bit of an issue with one of the methods I want to show you if we don't have any, if everything is positive and good. Okay, so what we're trying to do here is to find the area of the triangle whose vertices are at the points A, B, and C with those particular coordinates. How can we do that? What are the best ways of dealing with this particular problem? Okay, first of all, 4 methods, and this is method number 1. This method, I learned it while I was actually an examiner, a fellow examiner. When we were dealing with marking schemes, he insisted we put this particular method in the marking scheme. I didn't think it was a great method, but I learned something in my time there. So this is now what is this particular method all about. We're going to put the points A, B, and C to some correct relative position. So let's say that 2, 2 is here. That's the point A. Point B, 5, 10, let's say here and here. That's the point B, and the point C is 11, so it's to the right, and 6 somewhere up here. So that's the point with coordinates A, 2, 2. B is in fact 5, 10, and C is the point with coordinates 11, 6. And we try to find the area of the triangle A. Need to move so I can draw a reasonably straight line. B, C. Okay. The method that I don't know what how much I should call this one is it involves trapeziums, and I did say in the beginning I picked positive numbers not actually deliberately because these methods do not work with negatives. It's just purely because I thought it'll make the calculations easy. But this particular method, my colleague's method, it has a few snags if you have a mix of positive and negative coordinates. It's no problem if you're having, let's say, this 2 negative or this 2 negative, but if you have this negative and this negative, I don't see how you're going to adapt this method to work. So you'll see in a minute how you can actually do the area using the method using trapeziums. Okay, I'm going to draw some extra lines. I'm going to draw perpendiculars to the x-axis, but you could have actually drawn perpendiculars to the y-axis. Okay, so if you had just x or y coordinates which were negative, depending which ones are negative, you would have actually adapted your method. So I'm going to do the same thing here, and I'm going to do the same thing from that corner down to the x-axis. If you study the picture now carefully, we have in there 3 trapeziums. Let's spot them. One is here, this one here, another one is this one, and we have one more trapezium. This one is lying on its side, so it's like that. So clearly the area of the triangle ABC can be found by adding this trapezium to this trapezium, the areas of course, and then subtract the area of this trapezium. So the answer, let's check what it will be. This trapezium, let's put some measurements so we know what we got. We can pick it from the y coordinates first of all. These are the red lengths. That's a 2, that is a 10, and this red length is a 6, and we also need some lengths from there to there. Now look at the x coordinates. 2 to 5 is a 3, 5 to 11 is a 6, and I think that's all I need. And now we can go to the calculation. This trapezium, the area is going to be average of the 2 parallel sides, 10 plus 2, average multiplied by the height, which of course is 3. To that And we need to add this trapezium. So that is going to be the average of the two parallel sides. 10 plus 6 divided by 2, multiplied by the height of this trapezium, which of course is 6. And from that, I will need to subtract now the area of this trapezium. And these are the parallel sides for this. So the average of those two parallel sides is 2 plus 6. Take the average, divide by 2, and then multiply by the height, which of course in this case is a 9. All is left to do is a calculation. 12 divided by 2 is 6 times 3 is 18. 16 divided by 2 is 8 times 6 is 48. And lastly, 2 plus 6 is 8, divided by 2 is 4, 36. So 48 take away 36 is 12. 12 plus 18, I got the area as 30 square units. I hope you follow what I've done. It's not one of my favorite methods. I must admit, personally, I will never use this method because for something like that, there's a superior method to use, which in fact makes sense even to a year 8 when they say this is going to be a lot more complicated. And as I explained, there is a problem if you have mixed signs in your coordinates. Okay, try to look now at the method 2. This is my favorite method when I'm teaching sort of year 12s because the tools are limited and therefore there are other techniques that involve further maths that they don't have access to. But certainly I won't teach the trapeziums, but this is what I will show them instead. Let me rub off some of these things that we have so I don't have to draw the picture. So I'm going to take off all these red bits and let's study the picture again. Okay, I'm not making use, there might be some right angle there perhaps I mean, if the problem, for example, was something to do with lines and you have shown perhaps that there's a right angle somewhere in the triangle and you have looked at a couple of lengths, then probably that's a special cases. You can actually do base times height divided by 2 and use previous parts. But here I'm not making any assumptions that there's anything special about this triangle. Okay, how are we gonna do this now? Method 2. My method is boxing it, and boxing it means doing this. I'm gonna fit this into a perfect box whose sides are parallel to the X and the Y axis. Okay, I don't need obviously that up there. So now I'm gonna put some lengths. I'm looking first of all at how long is this side. I'm looking at the Y coordinates. 2 until 10, that is 8. And then what's that across? Is the X coordinates now from 2 to 11, that's a 9. And I've got to do this length, this length, this length, and this length. Look at the X coordinates from 2 to 5, that's a 3. And from 5 until 11, it's a 6. And 3 plus 6 is 9. Yes, it does agree, just in case we made any silly errors. And now this length here, I'm looking at the Y coordinates, 6 and 10, they're 4 apart. This should be a 4 to make up the 8, but let's check it. Look at the Y coordinates again, 2 to 6 is 4. And the game is up, because now this is much simpler and much easier. We have a rectangle in red who measures 8 times 9, which is 72, and from that we need to subtract 3 right angle triangles. Here they are. One measures 3 by 8. 3 times 8 is 24, divided by 2 is 12. 6 times 4 is also 24, divided by 2 is 12. And then we go 4 times 9, which is 36, divided by 2, this is 18. So 72, take away 12 is 60. So that's this bit here. 12 and 18 is of course negative 30. And of course the answer to that, you can use your calculator of course, is 30 units as before. So that was method number 2. And I hope you understood also method number 2. Okay, your choice of course, whether you're going to go with the trapeziums or something like that. Is there a third method for this? Okay, there is, but it involves knowledge from further maths. So we're going to look now I'm not going to show you a proof for this. I actually shown this particular method. Now, what was that? I have it up there, luckily, because I rubbed off things. And in fact, I don't even need a picture for something like this. Shall I just, let's leave this as we have it in there. Because the method number 3 and number 4 do not even require a diagram. It's all abstract algebra. Okay, so let's have a look. Point C had coordinates 11, 6. I have it up there, and this was a 2, 2. In a previous lecture, I don't remember what was the topic, but it must have been further maths. Actually, I do remember the topic. It was some kind of geometry problem involving an ellipse, a conic section, and he asked to find some area of a triangle, and we had to do it in a very long and painful geometric way. And then I showed you, okay, we can do that in 30 seconds using this particular method, which a lot of people don't know. The area of a triangle that has coordinates, let me just write it up here. So that's method 3. Picture not needed. If we have a triangle with coordinates, I'm not going to label them, x1, y1, in 2D of course, x2, y2, and x3, y3, like we have there. Okay, then the area of this triangle is given by this expression. The area is a half times a very special determinant. This determinant will have 1, 1, 1, and we're going to have x1, y1, x2, y2, x3, y3, and two things to mention there. Sometimes people, because they want the coordinates to be written x1, y1, they do write the 1, 1, 1 on this side, and then the coordinates x1, y1, x2, y2, x3, y3. It's okay, because of course determinants do transpose without the same answer. But there's one more thing. This may produce a negative area, okay? If it produces a negative, I should really put it here, but a lot of people that use this formula, they're aware of it. You're going to have to throw away the minus. All it means is your triangle is reflected, is flipped upside down basically. So this is the determinant sign, and this is the modulus. It looks a bit ugly and a bit weird. Okay, so let's find now the area of this particular triangle, and let's see what this thing gives us. A half times 1, 1, 1, coordinate number 1, 2, 2, coordinate number 2, 5, 10, coordinate number 3, 11, 6. We can evaluate this determinant, so this now involves further maths, and I'm going to do a little bit more further maths in this because I don't fancy breaking that into 3 different determinants, 2 by 2 determinants. So I'm going to use a property of the determinants, which is known as column or row operations. They're not the same thing. I can use column or row operations. Here I'm going to use column operations. So I'm going to multiply this column by -1 and add it to this column, and I'm going to multiply this column by -1 and add it to this column. This leaves the determinant unaffected. It's a property of determinants. I don't know if you've seen it before. If it's not, well, you're learning something. So that's the 125 times all of this by -1 and add it to the second. Times -1 times add to 1 gives me 0. That's why I've done that. Times this by -1, -2, that will become now a 3 when I add it to that, and times this by -1, -2, add it to that, it will give me 8. Same thing, back to this, times by -1. All I'm trying to do is to create zeros there basically, because it's easier in the evaluation. This will make 0 by construction, times -1 is -2, this will become now a 9 when I add it to 11, and times this by -1 is -2, add it to this, it will give me a 4. And this determinant now will have the following value. Shall I just squeeze it in here? I hope it's visible in the video, because I don't know what part of the board up to a certain level you cannot see. Okay, so this is now, area is a half. Of course, because of the zeros there, the only part that produces something is the minor of this, so it's 1, positive 1. That minus that, so that's going to be the modulus of 12 minus 72. And of course, surprise, surprise, 12 take away 72 is minus 60. The modulus of minus 60 is 60. Half of 60 is in fact 30. Okay, so this works very well and is very useful when you don't actually have numbers that you can perhaps do boxes and things like that. You can have expressions in sines and causes in all sorts of things. So this method is very, very useful. And I'm going to actually go to method 4. So that was the method that we used, the standard determinant. Method 4 is a method that further mathematicians, I think now this is in further maths, I'm not quite sure. I think if you're doing the basic further maths, this does not come into it. And you might make sense now. In fact, I'll say something at the very end where this is coming from. So let's shall I just leave that up there? Let's leave it. I'll try to leave it so we can actually see some of these quantities in there. Okay, it doesn't really matter the diagram for this one, but in order to follow this, we know that the area of a triangle, that's in further maths, whose sides are the vectors P and Q, the area is a half modulus of P cross Q, where this is the cross product or the vector product. So in our case, if you look at that triangle, nothing to scale, we got A, B and C. We might use, without losing any generality, the vector AB and the vector AC. Okay, so what will happen? The vector AB, first of all, is of course B minus A. And of course, I do apologize, I write my vectors as rows. People say, oh, vectors are not coordinates. Vectors are coordinates, thank you. And whoever argues with me can go away. I don't want to have an argument over it. I'm going to write the vector B as 5, 10. If you want to write columns, please do write columns. I'll write them like this. This is my vector 5, 10 minus A, which is 2, 2. All a vector is just an ordered pair. How you choose to order it is irrelevant. So that's a 3, 10 take away 2 is 8. Okay, so that's the vector AB. So that's this one here. The vector AC is needed next. And C minus A is equal to C, which is 11. 6 minus 2, 2. Will now give me 11 take away 2, which of course is 9. And 6 take away 2, which of course is 4. And therefore, the area of this particular triangle, whose corners are there, is given by the following quantity. Area is a half AB crossed. I do write my cross product like this. It's just an annoying habit I have as well. I have lots of annoying habits. Okay, so it's AB cross AC. And of course, this is now the modulus of a determinant. And the determinant is I.G.B. And I need to put the vector AB in. The vector AB is 3, 8. 3, 8. We're in 2 dimensions, there's no Z coordinate. So that's 0. And the other one is, of course, 9, 4, 0. So that's the determinant sign that evaluates this, and this modulus are put on the other side. Okay, let's have a look at this particular line and just spot something actually is transposed there because yeah, it's the same thing that is going to happen here. Okay, let's work it out and let's see what we're going to get. This is equal to a half. This is the modulus. Now, if you look what happens with the I component, 8 times 0 minus 4 times 0 is gone. If you look at the J component, we're going to have, of course, 0 minus 0 gone. I'm doing it this way for the J because it has a minus. And for the K component, which is positive, it's going to be 3 times 4, which is, of course, 12. Actually, I should really write it as vector. So that's 0 for the I component, 0 for the J component, and the K component is going to be 12. Minus 72, And of course, this is the vector, the modulus of the vector. If you prefer it, you can write it as a half minus 60k. And of course, the modulus of that is 60, and is half of 60, which of course is 30 as before. And what I want to say, of course, those of you who are doing further maths, they must have realized, even if you haven't seen this before in 2 dimensions, that this is nothing but a special case of this particular one. This is not really a special method. It's something that is good to know if you are having a 2D problem and you just want to simplify very, very quickly. There's no vectors involved, no subtractions like this to do. You just shove it into this particular determinant, and it only works, this particular formula, in 2 dimensions. If you want to prove it, by the way, as a challenge, you can actually prove this formula. It comes from here. If you just put x1, y1 and rearrange it and play around with it, you'll come up with this particular formula. Okay, and which formula is the best? Well, I'll show you 4 results in there. What would I personally be using if I was in straight maths, okay, or I was teaching rather in straight maths? I would be using the box method in 2D coordinates, just putting in a box and just working out the triangles around it. If I was in further maths, I would have used either this method if I was in 2D, but if I was in 3D, I have no choice, because this is the only method that works for the area of the triangle in 3 dimensions that I can think of at the moment. There might be more, but at the moment, that's the only thing that comes to my mind. Anyway, that's the end of this lecture. I hope you enjoyed it. I hope you followed it. Sorry I went a little bit too fast because I tried to make my lecture a little bit shorter. Okay, I'll see you very soon. Who's laughing now?